Hey everyone, I'm Tracy Delgado, and today we're going to talk about Module 4, Chapter 11, Transformations, Symmetries, and Tilings. And I always do a joke, but I'm not going to disappoint you this time. Which shape do you use to catch somebody? A trapezoid. So let's get started on our lesson. We have problem number 1. Ephraim and Devontae were asked to reflect the pattern block figure shown here over the horizontal line through the center of the square. They rearranged the blocks to form the figure on the right. What type of rigid motion did Ephraim and Devontae use? How would you help clear up their misunderstanding? Well, if we look at our shape like this, and then we look at what they've done over here, it's not reflected. They have rotated it to rotation. So if we're going to fix the problem, the horizontal line would reflect through the square and the figure would flip, keeping everything the same angle. In Devontae and Ephraim's drawing, they rotated it, making the triangles point in different directions. And this is the way we've rotated it here. Excuse me, we reflected it. We're not supposed to rotate it, we're supposed to reflect it. And this is our corrected picture here where it has been reflected and not rotated. Our next problem, we were given these shapes here. These two, I would call them Tetris shapes. Diamond, triangle, a half moon, rectangle, sideways triangle, and a hexagon. In our instructions, we are supposed to show one line of symmetry, but no rotational symmetry. Here's our lines right here for half moon, hexagon, half triangle, and rectangle. Our next one, we're supposed to show rotational symmetry, but no reflection symmetry. And that would be our two little Tetris shapes right here. We can rotate them 90 degrees, but they will not reflect. And you see the lines here, they will not reflect and be congruent with each other. So that leaves us our rectangle and diamond. When we draw the line of symmetry through here, you will see they will be congruent to each other. If you fold it, if it was like a piece of paper, you would fold it in half and they would be the same. And when you rotate, it would also be the same thing. Our next problem, Myra cut out a regular, pentagon, hexagon, and octagon. And it seems to her that they form a vertex figure. Well, let's see if she's right. This dot right here in the middle is where the three shapes come together, where they meet. In order to prove that this is a vertex figure, the interior angles need to equal 360 degrees. Now, if you remember from a previous teach we've done, the interior angle formula is n minus 2 times 180 divided by n. So for the pentagon, it has 5 sides. So we do 5 minus 2 times 180 divided by 5 equals 108 degrees. Our octagon has 8 sides. So it's 8 minus 2 times 180 divided by 8 equals 135 degrees. And our hexagon has 6 sides. So do 6 minus 2 times 180 divided by 6 equals 120 degrees. And when we add our three numbers together, 108 plus 135 plus 120, that equals 363 degrees. So that doesn't fulfill our requirement. She does not have a vertex figure right now. So I think we can help Myra get her vertex figure. If we insert a 3-degree gap in between the shapes so they are no longer touching, this will help her. We will take the 363 minus 3, and that will give us our 360 degrees. So here is her vertex figure. And on our next one, here's our shapes. It looks like a kite to me. And we're supposed to demonstrate why triangle QPT is congruent with triangle SPT. Well, if you look at them, if you were going to take PQT and then SPT, you see that they are congruent with each other. They will reflect. If you, like I said before, if you folded this in half, they would be totally even. They would match all together. And when you do angle QPT is congruent to angle SPT, I did triangles here. You see they line up, and if you would do the same thing with reflection, they will fold over each other, therefore making them congruent also. And the same would be also true with triangle QPV and triangle SPV, excuse me. They are congruent with each other. They reflect. And this would also be why angle QVP is a right angle. And I drew a little star showing everything I'm supposed to be looking at. Okay, problem number 5. We have penta. We have a pentagon, an equilateral triangle, and a circle, and then meet together with the O in the middle. And we are supposed to find the angle measurement for angle NOQ. So I made a triangle with 120, 30, and 30, and that will end up being a obtuse triangle. And when we inscribe our pentagon, we have 5x equals 360, and our x equals 72. And when we're finding our line NOP, as you can see right here, the angle for that is 144 degrees. So when we take 144 minus 120, that gives us 24 degrees. So angle NOQ is 24 degrees. And last but not least, we have Jenny here looking at this cliff. By holding a ruler 2 feet in front of her eyes as illustrated in the diagram, Jenny sees that the top and bottom point of vertical cliff face line up with marks separated by 1.5 inches on the ruler. Jenny is about 1/4 mile from the cliff. What is the approximate height of the cliff? And we need to remember that a mile is 5,280 feet. So what I did was I did triangles here. There's a little line right here. So I did ABC here and then DEF. And when we look at this, we see that A is congruent to D, B is congruent to E, and C is congruent to F. And as I remember before, 1 mile equals 5,280 feet. And when we divide 5,280 by 4, that equals 1,320 feet. But we need to get into our ruler here. So that's 1.5 inches right here. So when we do that, it's 0.125 feet. So we divide 2 over 1,320, that equals 0.125 over cliff. But that's not our answer. We are supposed to divide to find how far she is away from the cliff. So that's 0.125 times 1320 divided by 2, and that equals 82.5 feet. So Jenny is 82.5 feet away from the cliff. And I'm going to wrap up my slide with Yoda, and he says, in a dark place we find ourselves, and a little more knowledge lights our way. I wish everybody the best of luck through their teaching careers, and I will see y'all the next time. Bye.